Just as a warning, this procedure requires the use of sulfuric or hydrochloric acid, both of which are corrosive. Isopropyl chloride is somewhat toxic and may be mutagenic. A lot of fumes are produced, so be sure to work in a well-ventilated area. That said, let's throw on some gloves and goggles and get into it. Isopropyl chloride is a clear, volatile liquid with an extremely low boiling point of only 36 degrees Celsius. It belongs to a family of chemicals known as the alkyl halides, which have a variety of uses in organic chemistry, such as the Williamson ether synthesis or the Grignard reaction. I'm personally using this compound in the Worts reaction to generate an isomer of hexane, which is a major component of gasoline, but we'll see how that goes. Anyway, for this reaction, we'll only need 3 ingredients: sulfuric acid, salt, and isopropyl alcohol. I didn't show it here, but I also used some sodium bicarbonate to neutralize the product in a later step. Alternatively, the salt and sulfuric acid can be substituted for hydrochloric acid. You can also add some calcium chloride or zinc chloride as a catalyst, but the reaction works fine as is. To start, mix 250 milliliters of 93% isopropanol and 170 grams of salt in a large flask. I used a 500 milliliter boiling flask, but in hindsight I should have used something bigger. I recommend magnetically stirring the isopropanol as the salt is added to keep everything in suspension. Unfortunately, my store bar couldn't handle so much solid and it got bogged down after everything was added. Next, set up a simple distillation and charge an addition funnel with around 200 milliliters of sulfuric acid. I'm using some 93% drain cleaner acid that I bought at Walmart for around $5. I used an excess of acid because it seems to speed up the reaction somewhat. In reality, you could probably get it away with using only 100 milliliters of acid. Once everything is ready, turn on heating, crank up the condenser pump, and start dripping in the sulfuric acid. When the acid mixes with the solution, a couple of things happen. First, the acid reacts with the sodium chloride to produce hydrogen chloride. This hydrogen chloride then dissolves into the alcohol as it forms and starts reacting with it to produce isopropyl chloride and water. This reaction is reversible and tends to proceed slowly, so to help push things forward, we distill off the product as it forms. The distillation temperature doesn't need to be very high since the product boils just above room temperature. After a few minutes, the solution starts to boil gently and we can see vapor climbing the condenser. Not long afterwards, we collect our first few drops of distillate. The temperature shows we are near our target temperature, and within the hour we climb past 37 degrees Celsius. At this point, the smell of isopropyl chloride is quite noticeable. Smells can be somewhat hard to describe, but I would say isopropyl chloride smells similar to acetone but more sweet. It also tends to have a chemically, almost gasoline-like note to it. I would also like to stress that you should avoid inhaling these vapors as much as possible, since they are mildly toxic, possibly carcinogenic, and somewhat contaminated with hydrogen chloride gas. If you want, you can chill the receiving flask with an ice bath to help minimize fumes and evaporation losses. After distilling for around 4 hours, we end up with a nice sample of isopropyl chloride collected in our receiving flask. Unfortunately, the sample is somewhat crude and contains a lot of dissolved hydrogen chloride as well as water and unreacted isopropyl alcohol. To remove the hydrogen chloride, we wash our product a few times with saturated sodium bicarbonate solution. Be sure to do this slowly and with frequent venting and agitation to help control the bubbling. After washing, take the top isopropyl chloride layer and redistill it to separate any water or alcohol that remains. In the end, we are left with roughly 60 milliliters of reasonably pure isopropyl chloride. Weighing in at 52 grams, this corresponds to a percent yield of roughly 25%. There are likely a few reasons for such a bad yield. For one, a decent amount of the product overflowed off camera whenever I was doing the bicarbonate neutralization. Additionally, the reaction had to be cut off early when sodium chloride and sulfate started crystallizing out in the boiling flask. The use of a catalyst like zinc chloride could also improve the yield some. Now before I end the video, I want to take a moment to show off some of the properties of isopropyl chloride. First off, its flammability. Isopropyl chloride is highly flammable and burns with a dirty yellow flame as opposed to the ordinary isopropanol, which burns far more cleanly. Burning isopropyl chloride also releases a lot of toxic white smoke, so it's generally best to avoid burning it. One other thing I wanted to try was reacting with magnesium metal. In theory, isopropyl chloride should react with magnesium to produce isopropyl magnesium chloride, a useful Grignard reagent. However, even after a few minutes, I didn't notice any reaction. I tried kickstarting a reaction by heating it with a few drops of sulfuric acid, and this might have worked to some degree, but I have my doubts. Anyways, there you have it. Synthesizing isopropyl chloride from reagents found in your everyday supermarket. In a future video, I'll try synthesizing sodium metal using the magnesium reduction process detailed by Nerd Rage, and after that I'll try combining the sodium and isopropyl chloride to produce hexane. Until then, LabCoatz out.